after the. So I'm not sure whether everybody signed in yet, but it looks like we have a pretty good group today. And in fact, let's establish a few suggestions to make sure everything goes smoothly, everybody gets all their questions asked. What I'd like to do is, I'm Roger. I'll be your instructor today. A little housekeeping here. I like to save the chat for conversations that may or may not be necessary with the host, and then save the Q&A for conversations amongst ourselves. I generally keep a close look at the Q&A box, and when something comes up, if you'll type in your question, I will then answer live, so everybody will get the answer. And the only bad question is the one you don't ask. I might say we're going to cover that later, whatever the case may be. But in any case, don't hesitate to participate in the Q&A. That's why this is a live presentation. And my name's Roger. I'm a retired electrical engineering professor. Ever since before I retired, I've been active in the field of electrical contracting and particular licensed engineering, and most of that work has been in photovoltaics. So in fact, right now I'm working for a former student who has a photovoltaic engineering. We do permit packages, and in the last couple of years we've done about 4,500 of them. So we've done a bit of this, and I want to be able to share some experiences with you today, because this is quite an exciting field to be to be in. It might be interesting. I'm going to drop down my participant box here, and maybe just raise your hand, everybody who has any involvement with any part of photovoltaics or renewable energy. All right, yeah, that's encouraging. I'm glad to see 11 or 12. I guess I see 10 hands that are still up, 9 now. So that's great. We should be able to have a very interesting afternoon here, and looking forward to having discussions and getting other people's ideas as well. So we're going to focus on battery backup systems today. We'll do a little bit of try to do some design, go all the way through. Not a whole lot of focus on the structural part today, but we will put an array together and so on. What I want to, since this field is moving so fast, I want to try to focus on basics today. What really is a DC coupled battery backup system? What does ESS mean? What are some of the options? What about AC coupled? Things like that, so that as things emerge and continue to improve and to some extent get more complicated, to some extent get easier, as long as you got the right tools, you'll be able to do the job. And so we're going to work on making sure you got everything you need in your toolkit in terms of understanding how these things work. Because then when the code changes and you adopt a new version of the code, whatever, or whenever you get a set of plans returned from your local authority having jurisdiction, you'll be able to explain why it is what you did is the right thing to do, hopefully. All right, so with that thought in mind, let's move on. Take a quick look at what some of the systems are. There's a whole house backup is one of the kinds of systems. Let's see what that looks like. Looks something like this. So you got your utility connection there. It's coming into a control box that has a set of contacts that are automatically open if the utility power is lost. Because if you're going to have a battery backup system, it is not supposed to be feeding back power to the grid if the grid is down. So if the grid goes down, these contacts open, and within 2 seconds, your system is no longer supplying power to the grid. And the reason it happens so quickly is because most utilities are very responsive to calls, emergencies, whatever. And we want to make sure that we are not feeding back any power into the grid when somebody's out there trying to restore that distribution line that fell when somebody ran into the power pole or something like that. So that's one of the rules here. This IEEE 1547 says that if we have an IEEE 1547 compliant renewable energy AC source, that if the utility goes down, the PV inverters go down. So that in itself presents an interesting challenge, because if the inverters need the utility in order to operate, because they're utility interactive inverters, how do they stay on then when the utility turns off? Well, we'll talk about that and what's inside these inverters that makes them so smart and able to do that. So here's a whole house backup system. And as you can see, we are interrupting right at the meter, and we are providing stored energy, or maybe some instantaneously made energy from a PV system up on the roof. If the PV system can handle the needs of the load, then the batteries don't turn on until they're needed. The partial backup system will look something like this. And you notice here we're feeding a subpanel out of the main distribution panel where the interruptible loads are located. Boy, I don't know about my throat today. In any case, you can notice that the contacts that interrupt and disconnect the standby system from the utility now are on the load side of the main distribution panel. So the loads in the main distribution panel, the larger ones that require more power and more kilowatt hours, they're not operable. So it may well be you lose your air conditioning, you might lose your oven, you might lose a few things like that in the case of the utility being down, but that's simply because you've opted to store only enough energy to run a certain number of loads, and therefore, and also the energy storage system has a limit to the amount of power that it can provide. So if you got some high power, 12 kW range, if it comes anywhere near its rating, that's a pretty big challenge for anything short of around 30 to 40 kilowatt hours of storage. So anyway, this is where we're going, is to look at some of these systems and look at the basis of why they work, how they work, and what's been done over the last 10 or 12 or 15 years to simplify and improve them. So the utility interconnect rules are in the National Electrical Code, Chapter 705.12b, meaning that we are connecting any energy storage and the renewable energy source to the utility on the load side of the main circuit breaker. Okay, so if you do that, then that's it. We'll look at some various interconnects as well. So let's move on and talk about those inverters that are so fancy that they are smart enough to know when the utility is down and when they have to synchronize their own output to 60 hertz rather than depending on the utility to do that. And let's talk about why that is. Battery backup good connectors they serve multiple functions. If they are feeding the grid, then they use the grid voltage waveform as a synchronizing waveform, and they feed in current. They actually act as a constant current source. Well, not so constant when clouds come over, but in any case, they are current sources as opposed to voltage sources. So that means simply that if they want to contribute 20 or 30 or 40 or 50 amps to the loads, and maybe to the utility if the loads don't need that much, they'll be able to do that as long as there's a utility voltage that keeps the current waveform at 60 hertz. If the utility goes away, that current waveform doesn't have anything to synchronize it. It drifts off frequency, and it necessarily shuts down, because that's what IEEE 1547 and UL 1741 require it to do. Okay, so, and some of you in the solar business already know this, but if you're not, then this, of course, is probably the first thing you were wondering about when you turned on your computer. It's just, how do these things work? Now, if the grid goes down, then the story changes, because when they don't see the grid anymore, then they know, since they're in a backup situation, they know that they are the ones that have to provide the synchronization. So they then switch over and become voltage sources. And then any other inverters in the system or whatever recognize that there's something there that looks like the utility, whether or not it really might be the utility. And so if we're disconnected from the utility, but there's still something in the system that looks like it, the rest of the inverters are perfectly happy to do what they like to do best, which is convert DC solar electricity into AC solar electricity of perfect waveforms that is as good as or better than the waveform that you get from the utility coming in from the street or from the backyard. Okay, so if the grid is up and the sun is down and the batteries need some charging, they have the capacity to charge up the batteries from the grid when the solar is not doing that. The input to the inverters is the battery voltage, or in some case, the input to the microinverter is the module voltage. But in any case, most of these inverters, again, except for the microinverters, don't need to do maximum power point tracking. In other words, if you've got a solar module up there, you want it to produce as much power as possible, and you can incentivize that as such by doing that electronically and having the inverter or the maximum power point tracking portion of the inverter sample the power coming down from the roof, and then they reset the voltage of that they're picking up from the roof and see if they get more power by doing that, and they keep adjusting it and iterating it until they get on the maximum power. And they do that fairly frequently because that maximum power can change when clouds go over and so forth. So maximum power point tracking is really important. And if the inverter itself is not connected directly to the grid, then they don't have to do that. Something else is going to do that for them. Okay, so there's some of these inverters do maximum power point tracking, some don't. It's an interesting eclectic mix of things. Also, normally these inverters don't need to do ground fault detection, interruption, or arc fault circuit interruption, but sometimes they do have that provision within. They do need to be a part of a rapid shutdown system one way or another, so that if there's an emergency and somebody flips the rapid shutdown switch, the power coming down from the roof is relocated such that only the roof might be energized, and in that particular case, only the solar modules would be energized, and nothing outside of the array would be energized. Nice thing about them is they're pretty quiet, so they don't make much noise if the grid is down. And if your neighbor has a gasoline generator, they really appreciate you don't add any additional noise to the noise that their generator is making. And they save trips to the gas station if the grid is down. And given the situation we have right down here in Broward and Palm Beach County, Florida, maybe Dade County, I haven't heard, we've got a lot of gas stations that don't have gas right now. So even if we had gone to the gas station, we wouldn't have been able to get any. So this would be a situation where we do have electricity. And in fact, if we have an electric vehicle, we can charge it because we have electricity. But it's another interesting thing about gas stations and inverters. UL 1741 is the testing procedure that is required for them, their compliance. Otherwise, they're not allowed to hook up to the utility. So a lot of these actually have a separate input where you can connect an emergency backup generator, and they are smart enough to isolate the emergency backup power from the photovoltaic power or from the grid, because emergency fossil fuel generator backup power does not interact favorably with either the output of a photovoltaic system or the grid. And it's not that the emergency generator is going to hurt the PV system. It's the PV system. If it can overload the generator and try to run the generator backwards, they're not happy with that. So therefore, using emergency backup with fossil fuel is a special thing that needs to be thought about to make sure that everybody gets along with everybody else in the system. I see a Q&A up there. Let's see what we've got. Do the inverters act as a transfer switch such that when solar power and grid power is not available, switch to battery power? The answer is yes, they do. Sometimes the inverter itself does it. Sometimes there is a separate controller in the system that does the transfer switch. So it all depends on whether you're doing a microinverter system or whether you're using a single inverter type system. But the single inverters that we're talking about right now do have internal transfer switch, so it shuts down the inverter. You saw that switch on the diagrams earlier, where I had shown it inside a different enclosure. But these particular inverters, most of them, when there's no one else, no other controller involved other than that inverter itself, it takes over that control function. Okay, so yeah, good question. Good that you asked that. I appreciate it. Okay, so this is what we're expecting from a inverter when this is the piece of equipment that's supposed to do most of the work in terms of the controlling and routing and stuff like that. But like I say, there are systems, mostly either microinverter systems, and sometimes there are systems that have string inverters, but they may have other means of rapid shutdown that have to be, like optimizers, for example, and SolarEdge. So yeah, there's a lot of interesting stuff, and I hope we can cover as much as possible in the next hour and however many minutes we've got left. Looks like about an hour and 40 minutes. So the types of battery backup grid connected systems are the DC coupled systems and the AC coupled systems. And I'm going to let you save this to read it because we have some pictures of these. And generally, the pictures are worth 1,000 words. So let's take a look at them one at a time. Here's DC coupled system. It starts, well, wherever you want to, but let's assume we're starting with some solar modules up on a roof or out in the backyard somewhere. And these solar array, it makes a lot of DC power, probably at a voltage somewhere in the neighborhood between 140 and 600 volts. Depending on just whose inverter and whose equipment you're using. This array generally has a number of source circuits in it, anywhere between 1 and say maybe 8. And so we got a bunch of thin wires, typically number 10s, coming down from the roof to a source circuit combiner box, which is just like a distribution panel working backwards, because the power comes in on the skinny wires and then it goes out on the fat wires where it's combined, goes out to the charge controller. It's nice to have a surge arrestor in the system because that kind of stops if you have a surge coming down from the roof. It's nice to stop it before it hits some of this fancy sensitive electronic equipment like the charge controller, for example. In this particular system, the charge controller is what does the maximum power point tracking and make sure that the array is putting out maximum power all the time. And then charge controller, notice up to this point, there's only been a flow of power in one direction. But now we get to a point where the charge controller has the DC power coming out from the array. And that DC power has two different places it can go. It can either go to the storage batteries if they need it, or it goes to this fancy inverter we've been talking about, the battery backup inverter. It goes to its DC input. The one thing I don't show on that battery is they generally also have an input from a generator, and that's a one-way power flow from the generator. And that generator, if the thing is hooked up a certain way, the generator can be turned on to back up batteries. But generally that's not desirable because you want the sun to do that. It's very expensive to run a generator, typically $1 a kilowatt hour or more. And so why have the dollar per kilowatt hour gasoline generator charge your batteries when the solar array will do it for free? And maybe you need the generator to top them up a little bit at the end. In any case, the power goes in the inverter, and the inverter converts it from DC to AC. And the first loads you get a shot at this are the standby loads. If the grid is up, then the power can flow in either direction from the distribution panel where they are connected. That's where the solar is being tied into the utility. And as you can see, if the power from the PV that comes out of the inverter goes into the standby loads, they're perfectly happy. They've got all they need, and you've got some leftovers. Then it goes up to the distribution panel. And if all the loads there are happy and have everything they need, then the rest of it goes on out to the utility, and presumably gets sold to the utility for the same price you pay the utility from the electricity you buy from them. There are areas where the utilities are trying to change this practice, and there are areas where the utilities are quite happy to have this electricity at a time when they really need it. So interesting situations here. Normal operation here of the storage batteries is that they don't supply any power to loads when the grid is in operation. That's up to the grid to do that. But there are some changes as of 2020 to IEEE 1547, where now it is possible for the storage batteries to be talking to the utility. And at times when utility needs some assistance during peak time, the utility can request the storage batteries, please send some energy out to them and help them out. And if that is the case, then the batteries will export some energy. The energy coming out of the batteries doesn't necessarily make it to the utility, but if it reduces the load of the occupancy, that's in effect giving the utility some additional power to use someplace else. And that's not too different from the older load management things where the utility would simply control your water heater, your swimming pool pump, or your air conditioner and turn them off for a while to reduce the demand at a particular time of day. All right, so this is a DC couple, the advantages and disadvantages. The advantages, there's only one inverter, but it's kind of expensive. And that one inverter is generally somewhat less efficient than the one in the next system we're going to look at. We're looking at somewhere in the neighborhood 95, 96% efficiency usually here, and we're going to be seeing more efficient system elsewhere as we move along. But this is historically, this is the way it used to be done. The very first, I don't know, when we first started installing these back in right at the turn of the century, and started installing a number of them after hurricane seasons in 2004 and 2005. And this is the kind of system we had. There's typically 8 batteries with 8 kilowatt hours of storage, not very big, but they sure did. People kept their beer cold, and had microwave to heat other stuff up. And that made them different from their neighbors who had to drink warm beer after a hurricane. So, but keeping that refrigerator running, that was really a good thing. That extra cost of batteries maybe paid itself off as an insurance policy by providing power during utility downtime. All right, next one. This is the AC coupled system. Let's see, we have a Q&A up here. Let's see what we got. Can we get a copy? Absolutely. After the program is over, Keith, there will be a lot of information in the chat box on how to get everything. And these slides belong to me, and you have my permission to use them for any purpose you want to use them. The whole idea is to make sure people understand this stuff. And if I'm not the guy who does it, if you do it, that's fine with me. So just follow the instructions at the end of the webinar, and it tells you how to download the slides. And thank you for asking that question. I'm sure others may have wondered as well. Okay, so here we see this a little bit different. Notice here, the PV array, it goes immediately to a direct grid connect inverter. So the DC electricity from the array is immediately converted to AC electricity before it even gets down from the roof. In fact, before it even gets out from underneath the PV panels. And this AC then is fed directly down to the standby load panel. And sometimes this AC is first fed to a controller, which then sends it to the standby load panel, depending again on the system configuration. But again, this is the historic system, so you can understand the whole concept behind the DC coupling and AC coupling. Another Q&A, let's see what we got here. Where's electricity goes fed to the standby loads? The electricity that goes to the standby loads goes to the standby loads. If there are some, that might be where your refrigerator, microwave, and a few lights are hooked up. And that's a regular distribution panel here, an AC distribution panel. And you might have, say, a 40 amp circuit breaker tying in your PV to this distribution panel. And then you've got a bunch of loads in there that are going to be operating all the time, whether or not the utility's up. So we haven't even established that the utility's up or not. We're just saying that whatever comes out of the PV array, its first choice is standby loads. And once the standby loads are happy, the rest of it, as you can see, the bidirectional arrow between the standby load panel and the battery backup inverter, that's our same friend from the previous slide. And the secret here is that AC output to standby loads is just a connection. I mean, it's a set of terminals on a bus bar. So it's not just AC out. You can dump AC in there. And that was a tightly held secret for a number of years before people figured that out, because normally that AC out was to feed standby loads. But now the standby loads are fed by the PV array, and they go back to the battery backup inverter, which has a bus bar that connects to the distribution panel through the top of that connection. So that, and it also has the opportunity to charge batteries. So if the batteries are charged, then the excess power that's coming in from the standby loads goes up to the distribution panel. And if there are any loads there that want it, they get it. And if there's still leftovers, it gets sold back to the utility. A couple more questions. Let's see what we've got. Where's the standby panel? Oh, okay, I did that one already. And is the Tesla energy system yes, it is definitely an AC coupled example. It's got all these individual components are all crammed into a couple boxes. We're going to take a quick look at that at the very end. Okay, so yeah, we're going to see that, and it's definitely AC coupled. And in fact, this battery backup inverter is right inside of the Tesla Powerwall. And Tesla is also now starting to come out with inverters, and they've had modules on the market for a while. So yeah, we're going to take a look at that a little bit later. And do you need to make any prearrange with the utility for net metering? Yeah, you do. It's like any other PV system. You need to sign a utility interconnect agreement and with the utility, and they have certain rules about how you can tie into utility. You have to follow NEC 705.12 or 11, and if you're on the 2020 code, then you follow 11 and 12. And you have to have UL 1741 compliant inverters and equipment and all that kind of stuff. And as long as you promise that you're going to do that and give them a picture of what you've got, then every utility has a slightly different interconnect agreement. I've heard some get pretty complicated, but in any case, yeah, they won't tie you in until you sign an agreement. So let's see, what do we got? Did that one. And from PV to utility seems like 2 inverters in the path, which means lower efficiency than a DC coupled system. It would seem like that, but guess what? This battery backup inverter, it's just exactly what I thought when I first saw this thing, that my gosh, we're wasting energy in a battery backup. But the path between AC and out and AC in is just a bus bar. So there are no losses there. The only reason there would, and they don't have to change any AC to or DC to AC in there because that's done with the direct grid connect inverter. So you notice we're not using the DC in, well, but we are. See, the DC input of this battery backup inverter is where the storage batteries are connected. So the storage batteries are probably working at well, again, in the call them the heritage system, if you like, they all mostly ran at 48 volts. Some of the newer systems now run at 400 volts, and we're going to take a look at one of them as well. And it's true that not all utilities support net metering. And there's Jacksonville Electric and others. And that's one nice thing about the battery backup system. They have, some of them have ways of preventing any export, that you save it and you use it all yourself. Some people run their dryers and their ovens in the afternoon rather than trying to sell cheap electricity to the utility. So yeah, this is a big movement now among, Dave, that among the utilities. So Florida's got a number of utilities that have been trying to get rid of net metering. They even tried to get the legislature to pass a bill to eliminate it last year, but it was basically watered down to the point where it didn't mean anything. And so yes, it's an interesting challenge. But things are going to change. As I mentioned earlier, there will be times in the future, and mark my words, where the utilities are going to be glad that you've got a battery backup inverter that is compliant with UL, with IEEE 1547-2000 and able to export to them when they're in trouble. When they can't keep up with the demand, when the number of electric vehicles increases to 18.7 million in the year 2030, and all of them are hungry for electricity. Utilities, I think they're going to have to change their mind here pretty soon. They used to also support net metering, and even more than that. Some but in any case, you're absolutely right on that. And some people who realize that, they especially put in battery backup in order to be able to keep their electricity rather than to export it. So let's see. Gonna click these out so I can see my slide. And excellent questions, by the way. I appreciate everybody's awake and asking good questions. And I'm going to do my best to give good answers. If I don't know the answer is going to be, I don't know. So go ahead and do your best to make sure that any question you might have, I'll do my best to answer. Okay, so this is a little different configuration here, and it's actually more efficient because these direct grid connect inverters now, depending on whether they're single string inverters or whether they're micro inverters. The string inverters, some of them efficiencies are up in the 98 to 99%. So 98% of your PV array power finds its way to your standby loads with very minimal wiring loss, because usually standby loads are fairly close. The microinverters, pretty much the same story. They're in a roughly 97, 98% conversion efficiency, but there are a lot of other advantages folks see in them because they do maximum power point tracking at the individual module level. So that if you have a roof that has shade on 3 modules, all the rest of them are going to work fine, and those 3 won't drag down the performance of the rest of the system. So there's some real advantages there. Q&A. Let's see what we got. The direct implement, it all depends, James. The direct grid implement connect, the one I showed you doesn't, because the charge controller does. But when you lump all those subsystems into one single box, then the direct grid connect does implement the maximum power point tracking. Standby loads, community loads, yeah. I mean, the standby loads, the limit is, and we're going to talk about this a little later, about the batteries don't just have kilowatt hours, but they also have kilowatt limits on batteries. The 10 kilowatt hour, one of the 10 kilowatt hour batteries has a limit of 16 amps output. So that's where your limit comes in, is the maximum power that you can either put into the battery at a time or take out of the battery at a time without damaging the battery or shortening the life of the battery. So, but otherwise, the batteries don't care, and the inverters don't care. And if you have enough batteries, you can power the whole house. And then, for example, if you had 4 power walls, each one is good for 30 amps, actually for 21 amps. But that means you're looking at, you can have up to, they say that you can have the circuit breakers, if they're at 125% of the load, then the actual load, the circuit breakers, you can have 120 amps worth of circuit breakers fed by 4 power walls, for example. So yeah, it's the amount of storage you got makes a difference. That's the amount of power you can have instantaneously. That's the only issue on that. Let's see now. What type of batteries are typically used for storage? Well, the originals were definitely lead acid. We installed lots of those. There are some systems still that run at 48 volts with lead acid, but most of everything right now, I would say 95 or more % of the systems that we design to use battery backup are lithium based. So the lead acids, they are less expensive, but they're bulky, and if you're running, there's one system out there where you can have something like almost 500 kilowatt hours of storage at 48 volts. Well, if you figure out how many, the amount of current you're involving, you're looking at bus bars that are over 1,000 amp bus bars at 48 volts, and that's big time stuff. But there are some like that, and they're almost the only game in town for like commercial jobs where you want to be able to save a whole lot of stuff. Yeah, okay, Fortis lithium batteries. Good number. 185 amp discharge for 9,000 watts of power. Wait. 185. Oh, 48 volt. Oh, yeah. The 48 volt batteries can dump an awful lot of power. Certain lithium batteries can dump a lot of power. But most of the batteries that have electronics where they're AC out instead of DC out, they have current limiting, and they limit the output to. So what you that's a very good point, Dave, and thanks for bringing that up. That is one of the advantages of the 48 volt systems, is that they can dump generally a whole lot more power than you might want to get. On the other hand, 9,000 watts continuously is a lot of kilowatt hours. That's 9 kilowatt hours per hour. And so you're probably not going to, you got 18.5 kilowatt hours. So that's a 2-hour discharge rate, which is, that's acceptable for lithium, to discharge them in 2 hours. You wouldn't want to do that with lead acid. You generally don't want to discharge them in more than about, 5-hour discharge rate is about as high as you want it to be. Let's see. I love the questions. It's great. I hope we can make it through the. I have to say, hold on for a minute, folks. We got to get through this thing a ways. Let's see. We're 241. Okay, let's keep moving. But again, we're getting at the basics here, and that's what's important. That's what we're trying to do, is get at the basics, because the world is changing rapidly, and this is your basic structure, and all of these, except the batteries and the PV array, pretty much all the other boxes, the direct grid connect inverter, the standby loads. Well, that's going to be a different panel. And another distribution panel, but the direct grid connect inverter and the AC battery backup. Well, I guess the previous slide, a lot of the things are in one package, but these are pretty much individual enclosures that you see in front of you here. We put in a lot of Solarcs. Oh yeah. Oh, they are amazing. Yeah. Exactly. The Solarc does not have a separate outside controller. They've got, that sounds. We've got a couple people like that. We've designed a few systems just like that with 92 kilowatt hours of storage, and usually they're either huge residential systems, like 4,000 or 5,000 square foot houses that have 400 amp services. And but sometimes the commercial folks do this. But yeah, Solarc is the way to go. I mean, they've really, not that I'm advertising Solarcs, but they really do have some huge systems that are out there. And if you're looking for huge, you probably should take a look at Solarc and see just what they've got, because they've got some amazing stuff. Okay, let's see. Yeah. Okay, let's move on here a bit. Basics of battery backup design. And this is the old way of doing it again, but it's a nice way to do it. And I'll tell you in the new way after we go through the old way, but just a little history here. We used to list all the desired standby loads so that we knew exactly how many batteries we needed. And normally, as we listed all the desired standby loads, it was an iterative process, because normally people wanted a whole lot more to be backed up than was what made sense and it was practical. There were no whole house backup systems 15, 20 years ago. They're mostly partial backup with storage in the neighborhood of 8 to 16 kilowatt hours. So, and normally we're talking a backup for one day, as opposed to, say, an off-grid system where sometimes you size your batteries for 4 or 5 days of backup, depending on how much power you want to make in the wintertime when there's not much sun. But that's another story, and these are all grid connected. So normally, customary 1 day worth of storage is all it's designed with. Then list the variations in those standby loads. The ceiling fans, not so much used in the winter, but more lighting used in the winter, and so on. And list the months and estimate the inverter size, and then estimate the battery capacity and estimate the array size. I'm going through these that we're reading fairly quickly, okay? Here's where you decide. You want AC or DC coupled system? What's best? Typically, an AC coupled system is really nice when you don't need quite as much storage, and because your sunlight is being converted to DC electricity, or from DC to AC, with only 2% loss going to your backup loads. So if you're using most of your backup loads during the day, when the sun is shining, then you don't need the inefficiency of the round trip charging, discharging of the batteries. And that's where your losses are, is lithium, it's only about 5% you lose between going in and coming back out again. Lead acid, they generally figure 10% loss in and out. And again, it depends on the rate of charge and the rate of discharge, because the losses are I squared R losses in the battery internal resistance. And you're just heating up the battery, and the square, they're proportional to the square of the current. So these are average kind of things. anyway, you decide if you're going to have a lot of loads during the day and not so much at night, then AC coupling may be to go. Or the other thing is, a lot of people install a straight grid connect system and then they have a power outage and they don't have any electricity because they had to shut down. And that's an unhappy situation. So they decide, I want to add some batteries. Well, okay, fine, you can do it. You just add that extra inverter and interrupt you leave your array and everything the way it is on the roof. And then you can have your battery backup system by simply converting your straight grid connect AC system into a battery backup AC system. And we see that from time to time as well. And I imagine some of you do as well. So then you determine whether the system needs to be a three-phase system. In most residential situations, that's not an issue. But if it's a big one of those big solarcs, most of the inverters can be configured. If you use 9 inverters, you can have 3 per phase in a nice balanced three-phase system. So the answer is, can you back up three-phase systems? The answer is absolutely. So let's just do an example here quickly. Here's a quick Q&A. Let's take a look. Tesla Powerwall round trip efficiently about 90 to start and 70 to 80% at year 10. Oh, yeah, okay. Now, Tesla Powerwall's ever so slightly different in that it's AC in, AC out. And if you, that includes the losses in the AC to DC conversion for the battery charging, and then the inverter that brings it out again. So yeah, and again, the losses are less under lower loading than under high load conditions because the I²R losses are proportional to the square of the current. But good observation, Mark. Appreciate it. And yeah, so again, it's kind of like how you drive your car. If you race up to a stop sign and then slam on the brakes and then leave a little rubber behind when you take off to get across the intersection first, you're not going to get as good gas mileage as if you do that slowly. And same thing holds true with batteries. If you overwork them, they're not quite so happy. So they consume a little more of their own energy to keep themselves happier or whatever, however that works. I'm not sure. But yeah, thanks for that information. Well done. So let's build up, let's fill up an emergency standby panel here. That we can't really call it an emergency panel because emergency power, believe it or not, according to certain standards, has to be fossil. Even though a PV system will take over and run that breathing machine in milliseconds, and a standby gasoline generator that you have to haul out of the garage, fill it with gas, connect it up, flip the transfer switch manually, and takes 2 hours before you get that going. That can be an emergency power source. I find that a little bit ironic, but that's just the way it is. It is what it is. So we call these things standby loads, not emergency loads. And we don't dare do that, or the fire marshal or somebody gets upset with us. So we just kind of avoid that. So we look at the refrigerator, and you know, this whole business of refrigerators being 1,500 watts is it's a pretty good joke. If you look at the yellow sticker on it and see how many kilowatt hours it uses a year, and divide that by 7,760 hours in a year. Is that what? No, not 7,760. What is it? 8,760, 24 times 365, whatever that is. You're going to find out that refrigerator is really only pulling somewhere around 200 to 300 watts probably. In your microwave oven, maybe it's a smaller one, 900 watts instead of 1,200. Well, you take your nameplate things off these various things, and here we come up with these loads, 3,424 watts. So we got to size our batteries accordingly so that they will deliver 3,424 watts, like what you were talking about with the Teslas and with the Solarcs. They certainly would fill the bill for this one. And then you decide which load these are going to be on, whether they're 120 or 240 volt loads, and then we figure out how long we're going to operate it every day. And the daily operating time times the power gives us, and the power in kilowatts gives you the kilowatt hours. So as you see, we have a total of 16 amps as the maximum current on line 1, 12.9 on line 2, and we're going to need 7.65 battery kilowatt hours a day from the batteries. And maybe this will just be needed at night if the array has enough power to run the loads without the batteries during the day. Anyways, this is the starting point. Now, to be honest with you, nobody starts this way anymore, but this is good background to realize that this is what you're doing when you do backup. You're trying to imagine how much power do you need? And if you do this, it gives you a really good idea of exactly how much backup you need and exactly what your inverter powers have to be. Okay, so moving on. Now we can select an inverter. And we know it needs to do 3,424 watts. And we know it has to have 16 amps going through it to meet the load on L1. So if we have 120, remember I mentioned that that's just a bus bar between the AC in and the AC out. And so if that bus bar is capable of handling 50 or 60 amps, even though the inverter itself doesn't generate 50 or 60 amps, we can have the loads in the standby panel up to, whatever. And when the grid is up, we can feed all those standby loads happily as much as we want during the day if that standby panel is on a 650 amp breaker. So when the grid is up, we just don't want the load in the standby panel to exceed 50 amps. But when it's down, it shouldn't exceed 16 amps. Okay. But that's in the code. It says that you wire your house just as though the utility is going to be there. But if the utility isn't there, the replacement power for the utility does not have to equal having a utility in your backyard. It can be whatever you can stick in there, whether it's a gasoline generator or whether it's some photovoltaics. All right, and this inverter probably will use 48-volt battery pack, and it probably needs some external ground fault detection, interruption, arc fault, and stuff, which will be in a charge controller. Again, this is all this stuff is inside one box in today's systems. What do we got? Multiply it out, 365 times 1.15. What do we got? The question is, are you saying your refrigerator only operates 1.15 kilowatt hours a day? 365 times 1.15, and that's 419.75 kilowatt hours a year. And if you look at the yellow energy, what's it called? Energy, whatever sticker. You can buy a refrigerator that will run on that. It's not going to have all the bells and whistles of a big 25 cubic foot thing that gives you ice cubes and water in the door and whatever. But this particular one is a smaller one. And you can find one that will do that. It's hard to believe, but refrigerators have become a whole lot more efficient now than they were 20, 30 years ago. And this is one of the points I was making earlier. I think that energy, I don't know if that was this morning, but energy efficiency is making a big difference in what we can run. We can run a lot more now than we used to be able to. Now, let's see. Table's great, big eye opener for most people. They'll use 35 kilowatt hours a day, 45. Yeah, that's the point. This is not a whole house backup. This is a standby loads, and if you want to do a whole house, then you got to do that 35 to 45 kilowatt hours a day, which means you're going to need somewhere in that neighborhood of storage, not that much necessarily, because if you have enough PV on the roof to run some of your stuff directly with the solar, then you just need the batteries some during the day, but mostly at night. So yeah, and so that's why anybody doing a whole house backup, even on a whole house, they'll sometimes put in 20 kilowatt hours of storage, but they realize that they are not connected to the utility when they do that. They still have to be very judicious as to their choice of which of those whole house loads they want to run. So, I mean, you're absolutely right, Dave, on kilowatt hours a day. And if that's what you want, then you're going to have to upgrade your storage to come somewhere close to that. So another well-established point, you add some margin in this calculation for extras or stuff you didn't consider. Went through 60-hour interruption 6 weeks ago and came up with new ideas of loads. And I mean, yeah, the whole point is you can add some margin. This is giving you a starting point. And if you want more than that, you can do that. It just tells you how much additional storage and how much additional generation capacity you might need in order to make that happen. So, and fact of the matter is, most systems that we're doing right now actually do a whole lot more than what we're talking about right now, because people want the 20, 30, and 40 kilowatt hours of backup. And a number of them, I don't know, I had a couple in that range within the last week, in fact. So yeah, people, some, these things aren't particularly cheap. You're looking at somewhere $12,000 to $15,000 for a 10 kilowatt hour battery pack of lithium. So there are certain limits as to what people can actually afford. And then they do take up some space on the wall or next to the wall. So everything has constraints in these days, and you just need to make sure you're working within the constraints. Where are we getting to 1.15 kilowatt hours a day? I got that from the yellow sticker on the refrigerator. You just divide the annual by 365 and whatever it's rated at. Now, if your refrigerator used more, this is an example. So if your refrigerator used 10 kilowatt hours, then that's what you got to put in the table. Okay, so we're talking about a baby refrigerator that uses not a whole lot of electricity, but it'll probably keep some important medicines or whatever you might need to have in your refrigerator. They're there for you. So, but the way you get it is whatever is on the yellow sticker. And somebody maybe will remind me, what is this yellow sticker called? It's the energy guide, I think. And where you compare refrigerators, see which ones are the most efficient. And if you find your most efficient refrigerator, it'll surprise you. If you divide by 355, it isn't very much per day. Okay, let's see, inverter. We're still trying to select the inverter. Let's move down here again. Needs to be capable of charging batteries with the grid. Might use external DC and AC enclosures. All right, lots of possibilities for the inverter. I want to move a little quicker here. You're going to get data sheets, and most inverters and most pieces of equipment have a 2-page data sheet where they put all the numbers that are important. They don't tell you how to install it. That's in the installation guide, but the data sheets are generally have a lot of good information. And so we're looking at 2 inverters. One's an 8,000 volt amp and one's a 4,000 volt amp as possible options for, and these are not Solarcs, but they're a lot like Solarcs, and they could be Solarcs. I think these are, I don't even remember which ones these are. I forgot which ones I used. But these are the technical specs that came with these 2 possibilities. And you can see they give you instantaneous power for 100 milliseconds, surge power, peak power, continuous power. And it's a continuous power that really counts. And again, if you're using 4,000 volt amperes, that's 4 kilowatt hours per hour. And so that's going to drain your batteries pretty fast if you keep your load at that level for very long. That's an interesting exercise to see what's your average load over 24 hours with whatever storage you've got. And obviously, if you have 24 kilowatt hours of storage, your average over 24 hours can be 1,000 watts. But without that much, your average consumption is going to be about a lot light and a lot less than that. So thank goodness for LED lights and efficient refrigerators. A lot of information, DC input voltage. In other words, you got your spec sheet, you look at it and you find out which one matches up. In this case, a 4,000 volt amp unit matches just fine. Here's a question. What do we got? What are typical or examples of inverter vendors, manufacturers? Well, let's come back to that one, Bob, because the inverter manufacturers that are actually being used are not the ones that I'm showing here are examples of how the system works and then how that is implemented with today's equipment is going to be coming up later on. So we'll cover that in a little while, okay? The inverters that we use most of the time are the Enphase, and they're generally the IQ8 series. They're extremely popular these days, and we'll come to some of those. Okay, now we need batteries. We got ourselves a 4,000 watt inverter. We need 7.65 kilowatt hours. That is to the loads now, okay? That's not to the battery, that's to the load. So what do you have to put in an inverter in order to get 7.65 kilowatt hours out of it? And the way you do that, you got to look at some wiring losses, and you got to look at some losses within the inverter, and we need to divide by those because this shows we need 8.3 kilowatt hours at the input of the inverter in order to get out 7.65. And that's assuming we've got sort of somewhere in the neighborhood around 92% efficiency overall for the system. Okay. So now, how many amp hours do we want from the batteries? Because, well, some batteries and all the modern battery systems, the ESS systems, they're generally specified in terms of their kilowatt hours. But if we're doing ampere hour batteries, then we're going to need about 8,300 watt hours, okay? And if we divide that by 48 volts, that's 172.9 ampere hours to the inverter, okay? Now, you never want to drain your batteries down below 80% or down to 20%, below 20%, although, I mean, that damages lead acid, but you can do that with lithium. It's just that lithium doesn't particularly like it either. Their voltage drops a lot when you get below the 20% level. It starts dropping faster. But they'll work down to 10% or so, and then they decide they don't want to shut down on you. And so we have to divide by that 80% to make sure we're not using the full charge of the battery. Otherwise, the lead plates all turn into lead sulfate, and it makes it really hard to charge them anymore. So instead of 172, we need 216 ampere hours. Well, that's okay too, because there are some very nice, if you have 1 day of storage and you want to discharge it at, 24 hours, the C over 24 means the 24-hour discharge time. C over 4 would mean a 4-hour discharge time, and C over 0.5 would mean you're discharging, or 2C would mean you're discharging in a half hour. Not very many batteries are happy being discharged in half an hour. So you want deep discharge batteries, whether they're lead or lithium. We're looking at 216 amp hours that we need. And if it's lead, the 216 amp hour 6 volt is a pretty common size for a number of the deep discharge lead acid battery folks. And you'd need 8 of them in series in order to get 48 volts. And a lithium battery pack typically will come at a 48 volt rating. So you just need to check the voltage and kilowatt hour ratings on your lithium battery pack if that's what you're going to use. Lithium battery packs also generally come with their own battery management systems within, because it's very critical that every cell within that lithium battery pack, and there are lots of them, they all have to be charged equally. So there's a lot of series parallel connections in there, and in order to make those work the way they're supposed to. And you don't dare overcharge the lithium pack. You can overcharge your lead acid and it gives off some hydrogen, but The lithiums are pretty fussy about how they're charged. On the other hand, the managed charge management systems are pretty effective. And we just said that. So what about the discharge rate? We should talk about that. Here's a question. Let's take a look at that. Oh, AGM. That's an old lead acid term, stands for absorbent glass mat. Okay, and it's simply, rather than having an electrolyte that sloshes around, it's got some stuff in there. There's two types. There's the AGM and there's the gel to keep the electrolyte from just that sulfuric acid from sloshing around. So it's just a type to stabilize the electrolyte, even though it's basically a liquid. It can be either a gel or it can be like a bunch of, I don't know what the mat, it's like a glass mat. That means it's like fiberglass or something in there that prevents the sloshing around. Another good question. We should have a prize for the best question. Is there a typo? 8 6-volt is parallel to get. Did I say parallel? My goodness, absolutely that's a typo. That's stupid. You need them in series. Robert, you're a genius. Thank you for finding that. I think I have to change that. You're the first person. I don't know how many times I've given this webinar, and you're the first person to notice that I screwed it up. You all must have had a lot of coffee for lunch today. You're wide awake, and I can't tell you how much I appreciate that. Wow, thanks for catching that. That's unbelievable. I was said parallel. I mean, teach electrical engineering for 35 years and can't tell the difference between series and parallel. Sorry, guy. Problem there. Okay, design calls for take 24 hours to remove 80% of the battery charge. That's what we're talking about. And if that happens, that means your average power over that 24 hours is 345.6 watts. Well, of course, you're not going to do that. It's going to go up and down. You're going to want to run that 1200 watt or 900 watt microwave and so on and so forth. So it's going to go up and down. But it's probably going to be limited to that 16 amps. Okay, so this stuff, I guess I've mentioned most of this stuff before. 34.6 amps is kind of the most you want to do with these batteries. That's a 5-hour discharge rate. And that's 34.6 amps times 48 volts is 1660 watts. And that'll cover the microwave, but not a whole lot more than that. You're certainly not going to run your electric water heater, your dryer, or much else. There's certainly going to be 1600 watts is, well, 16 amps. It's not even 16 amps. The point is, we're looking at small loads here, but lights, you can run TV, lights, computer, a number of things. It's surprising what you can run. Anyway, you kind of want to schedule those standby loads because otherwise you can run out of batteries or make your batteries very unhappy if you're trying to work them too hard at any one time. And otherwise, you just need more batteries. All right, sizing the array. Question, let's take a look. Oh, you messed it up. Oh my goodness, Robert. I was going to go back and look at it, don't worry. And at least you proved that we're both awake. And that's always good. All right, so we're looking at batteries delivering 8.3 kilowatt hours a day. So we're going to have to charge them up with at least 8.3 kilowatt hours every day. If we got a round trip efficiency of 90% on the batteries, we've been talking about that, then we're going to have to put in 9.22 kilowatt hours a day to get 8.3 out. And so now we just need to figure out a solar array that will give us 9.22 kilowatt hours a day. And in fact, forget about all these losses and stuff, because what you're really going to do is you're going to go to NREL SAM or some other simulation program, and you're going to say, hey, I've got a roof that faces southwest with a slope of 18 degrees, and I want to make 9.22 kilowatt hours a day. How much solar do I need on that roof? By the way, I live in Tampa, or something like that. And So you do the simulation, it'll tell you how big your array has to be in order to do that, to put out 9.22 kilowatt hours a day of DC. All right. And but in other words, the simulation program takes care of all this loss calculation and stuff for you. Okay. And the losses are there no matter what. So here's your SAM. You go there, just Google Admiral SAM if you haven't already done it. It's a lot of fun. If you get tired of watching TV at night, it's fun to simulate PV systems. Although there's some pretty good TV on these days, I have to admit. All right. Well, anyway, what SAM gives you is basically what would normally come out of a maximum power point tracking charge controller. That's the bottom line here. So that's a nice way to size your array. And here's an analysis. Tampa, 18.43 degrees. I probably have it looking south here on this simulation, but who knows what direction it's going to look. It can look almost any direction and be economical these days. 9.22 kilowatt hours a day, 286 kilowatt hours in a month. And then we start asking, okay, when is the month we're most likely going to need this? And maybe that's September. And so you put in a 1 kilowatt array in the simulator and find out what that'll do for you. And that'll make you 1,475 kilowatt hours a year. And it breaks it down by the month. So 134 August, 119 September, 121 in October. Okay. Excuse me. And we'd like to have that 286 up in September. That's when we're most likely to get hit with a hurricane. You know, y'all might be more concerned about ice storms or other things. So then you pick a different month. So scale it up. It's linearly scalable. So instead of having 1 kilowatt, we need a 2.401 kilowatt array. And that's pretty small. I can tell you most of the arrays that we're designing for residential, the average is about 11 kW. So 2.4 is nothing. And maybe that, you know, that's 3,540 kilowatt hours a year it'll make for you. It makes 322, 286. Now, what if you want to make sure that you're covered for every single month? Well, then you want to make sure that you've got the 286 kilowatt hours every month of the year as a minimum, not just September. So you look at some of your other months and you discover that, well, gosh, you want to do that every month. In August, September, October, it won't do 9.22 kilowatt hours a day. In January, February, I'm sorry, it will do okay in August, September, and October. But in January, February, November, or December, forget it. You're not going to get 9.22 kilowatt hours a day out of this array. We got to upsize it. So take a look again at the simulation. And we need to bump up for the worst month. In December, we have to increase it from 222 to 286 in order to have what we're looking for. And so we need to increase the array by 286 over 222, or about 29% more. So now we've got 3.1 kW array, which is still a miniature array. I mean, it really is very small compared to what's being done. So what we have here then is a system. If it were 3 times as big, we could back up 3 times as much. So this gets us off to a good start as to what the possibilities are. All right, 449 kilowatt hours are able, annual 4570, and so forth. So what are the constraints on the array? Well, a charge controller, if you're using it, you can't do more than 3,200 watts, so you're going to need 2 of those. Maximum input voltage 150, so you got to limit the number of modules you put in series. There's losses. The array is never going to work at 100%, so you can increase the array size by 30% above 3,200, and it's not going to hurt anything. So it's not a bad idea to do that, because then you get by with fewer charge controllers and you don't lose anything. Because if your array ever puts out more than 80% of its rated power. Now, why is that? Well, first of all, the sun shining directly on it, it's going to get hot. Up north in the fall and the spring, you can maybe get a little bit more, but down here in Florida, if we shine sun directly on a ray, we're going to lose about 20% of the possible output just because of the negative temperature coefficient on the power production. So that's something you need to realize, that the hotter the module gets, the less power it's able to generate. It's too much is being converted to heat and not as much into electricity. All right. So anyway, the maximum DC output current from this charge controller is 60 amps. Okay. And when the array is cold, it has to have the open circuit voltage less than 150 volts. So that limits the modules that you can have in there. So let's take a look at some modules. We got A, B, C, and D, 235, 320, 350, 390 watt. I mean, we're using 460 watt modules now on some residential. So, you know, these are a year old, some 2 years old, but they're out there. You can still buy them. You have to figure out what can you do to be less than 150 volts. And here's all the parameters that are important. There's short circuit current, open circuit voltage, maximum power voltage, maximum power current. And here's your temperature variation of the open circuit voltage and your temperature variation of the maximum power voltage. Maximum open circuit voltage occurs when it's cold. And therefore, we need to look at what the output of the array is going to be when it's cold outside to make sure it does not exceed that 150 volt limit. And we have to make sure that it's not less than the limit allowed on maximum power voltage. Folks, I've got to take this. This is the boss. Hang on just a second. I'll be back. All right, so sorry. And so, okay, here's a comparison of 4 modules, and we just want to decide which one of these might work best. And here's a question. Well, yeah, she's away, and we're a 1-car family, and on her way home, and I want to make sure that she didn't have a problem. So yeah, Walter, thank you for asking. Okay. Well, looking at these, what does it look like here? Well, let's go to the next slide. And because we need to look at temperature corrections. And this looks pretty messy, and it is. And so I'm going to just say, if you're really interested in this stuff, then look at it after the webinar. Because if you look at the one in red, that's kind of a nice choice. When it's cold outside in Tampa, the open circuit voltage is going to go from the rated value of 41.18 to 46. And that's not a whole lot, you know. I mean, that's 5 out of 40. What's that? 8%, something like that. No, 5 divided by 40. No, that's more than that. And maximum power voltage when it gets hot is going to drop down from 33.5 to 28.3. Now, this is one, nobody does this anymore either. because everybody uses microinverters, and this is all taken care of by having the input quantities of the microinverters meet the output parameters of almost any module you might want to use. So, but this is what's happening when you're trying to make these decisions, okay? And if you were using a straight grid connect inverter with these modules. So let's move on past this and get on to some of the good stuff. Not that this stuff isn't good. And like I say, we're trying to come up with some background information so you can appreciate what we've got on hand now. But what if you understand history, sometimes if you understand what happened in World War II, for example, then maybe that makes you understand better something else. So this is history, but it's what people had to do 15 years ago. And it's being done for us now for the most part. All right, so let's get how are we going to wire that source and output circuit? Well, source circuits, that's the stuff coming down from the roof. And all we need is 156% of the short circuit current. And if we have a bunch of wires in a single conduit, then we may have to use a conduit fill D rate or a temperature D rate, depending on where the wires are run. And so then this number 10 wire, instead of being rated at 35 amps, it's only good for 27.59. On the other hand, it only needs to be good for 17.11. And fact of the matter is, you can use a 15 amp fuse on that, because you really just need to fuse it at, well, it's not a bad idea. 15 amps is going to work. And the output circuit, that's where you combine everything. You end up with the 60 amp fuse and number 6 wire. All right. And again, this is kind of the old way, but again, it helps you to appreciate where we've come from and where we might be headed. Okay. So this is module C. And you either take the larger of 1.56 times the short circuit current, or 1.25 times the short circuit current derated for temperature and conduit fill. And so that gives you the 27.59 for the wiring of the circuit. Okay, and need check voltage drop if the circuits are long, and we're not going to do all that stuff. Here's your voltage drop calculations, all this kind of stuff. And you just put all this into if you're still doing this, you put it into an Excel spreadsheet. And so here's maybe your array up on the roof. We ended up with a dozen modules. Again, that's a pretty small array. And you do a wind load calculation, and depending where it is, make sure that it won't blow away. And then you calculate your standby panel. I'm doing this quicker. I want to get up to the new stuff. And then you make sure you do all your bonding and grounding the way it's supposed to be. And again, if you're going to use some of these older things, this is a reference for you. But I want us to move up to some of the fancier stuff. Okay. So you need arc fault protection, because there's more than 80 volts on the DC side. Junction box is nice to have 90-degree terminals in the junction box, and you can rate your wires at 90 degrees. If there's 75-degree terminals, 90-degree wiring has to be used as though it were 75-degree wiring. So you kind of waste that THWN2. Okay, so here's volts and stuff where you're going to program the charge controller and the inverter. Let's say you want to make a bigger system, 120, 240. It might might look something like that. This is the total system diagram, and we're showing this as single line diagram. But this is basically the system. Let's walk through this so we can see what we have. Got modules up on the roof. They're connected in series, 2 strings of 6. All right, and they go down to this source circuit. Actually, they're not 2 strings of 6. They're 4 strings of 3. And because we're keeping the voltage below 150. So we're going into the source circuit combiner box. And we got 4 15-amp fuses there, 1 for each source circuit. And you can see the minuses go to a negative bus bar, and the ground goes to a ground bus bar. And these all go into this DC component enclosure where there's ground fault detection interruption device and a bus bar for the high current DC, and circuit breakers for input and output of the charge controller. It goes in at 60 amps, but it comes out at 80 because the charge controller doesn't lose any energy. It just is basically as a DC to DC converter that converts the input voltage is in the 60 to 70 volt range, and the output voltage, that's when the modules are in their operating condition, warm and all that stuff. And output can go up to 80 amps. You need an 80 amp circuit breaker on it. But input voltage times input current equals output voltage times output current. And we got a 175 amp breaker at the input of that inverter, so we can handle some starting current for some motors. So we got fat wire there. That's generally 3 or 4 watt battery cables. Then the AC input to the inverter that goes to this bypass setup here. And this, don't use these very much anymore either. But what this, but the Solarc does, they recommend that. And the whole idea is if you do any maintenance on the inverter, you need to be able to bypass the inverter to keep the standby loads running. And so this is basically an 80 amp going to the AC in, and then the AC out either comes out of the inverter and goes to the standby loads, or you can see that 160 amp breaker is a short circuit between the AC in and the AC out. So if you shut down the inverter, then you can short that out, and that's a gang switch, so it does 2 things at once. It either opens the top half and closes the bottom, or opens the bottom and closes the top. So that's just if you need to maintain the inverter. And earlier on, they needed a little more maintenance than they do now. Most of them are guaranteed for minimum 10 years, and sometimes as high as microinverters are now guaranteed for 25 years. So you don't have to fix much once you've got it installed. Let's see, check my Q&A there. So in any case, here's a way you can simplify that DC coupled system. Just like this, you put all that stuff inside of one box. So you got a 5 kVA, 120, 240 volt battery backup inverter. You have 24 amp continuous output current. You got a source circuit combiner with maximum 20 amps to the charge controlling. Charge controller with 250 to 600 volt maximum power point tracking. No more of this 150 volt stuff. You can go up to 600 now. Arc fault and ground fault integrated. You can do either charge the batteries by utility or by the PV, but you can even establish a priority that says do it with the PV first, and then if it's not done, then use the utility. So that's a nice feature. Multiple battery options, multiple operating modes, lots of grid support, including, and that's what I was talking about, that one day the utilities are going to be happy that people have installed these, because they're going to be sending a message from the utility by way of whatever communication method is adopted to this battery backup system saying, I need some electricity, can you please provide some? And the system says, what will you pay for it? And the utility says, well, and within a few hundred milliseconds, they've negotiated a price for this power you're going to sell back to the utility. And time of use optimization, all kinds of good stuff, all in one box. So, but now you understand what all those things do inside that box. And if I just brought this to you at the beginning of this show here, you'd say, what in the world is this stuff? But now you're looking at it and say, oh, I know what all that stuff is. Wow, I'm sure glad he did it that way. At least I hope you're saying that. That's the whole idea here. So this is at least one. And this one has a PV array of 600 volts max. And some of these, there's a couple of them out there. Generac is one, for example. And they run the PV array and the batteries at the same voltage, around 400 volts. And you know, instead of 200 amps coming out of the batteries at 40 volts, you got 20 amps coming out at 400. Same power. A lot thinner wire, a lot easier to wire, a lot easier to wire up. And that's just because not that the batteries themselves are that high rated, they're simply a DC to DC converter in the battery pack that converts the 48 or whatever voltage the batteries are at up to 400. So this is one of the things that's there that you can use and see. You just connect your PV array up the top, your maximum power point tracking is already there. Connect it up to the main utility panel, connect it up to a backup panel, and connect up your batteries and go home and watch TV. And you're all done. That's it. Well, maybe a little more than that, but still, it's a whole lot neater. In 2021, here's a 2021 version of DC coupled grid connected battery backup system. Okay. You got your interruptible loads here, and you've got an inverter. You got a PV system here, and you got DC storage over here, and down at the bottom you got a standby panel. Just that simple. An inverter, PV system, DC storage. Now this PV is going to have some rapid shutdown gadgets in line. Whatever the inverter manufacturer recommends you put in there. So there's a few parts missing here. There may be some AC disconnects and fuses, a few other things. You notice this does not show an AC disconnect other than the circuit breaker in the main distribution panel. And some utilities, if you're over 10 kW, some utilities, this is okay. Most utilities, if your system rating, AC rating is over 10,000 watts, you need an extra disconnect between the inverter and the main distribution panel that you can lock in case your PV is putting way too much electricity into the grid or something like that. Okay, so PV strings are DC, but this particular system is by the company that likes to use DC to DC optimizers. So therefore, you're doing maximum power point tracking at the grid level in this particular system, and right at the module level. Q&A, let's see what we got. I don't see this wiring diagram in the slides. That's interesting. If you're following, if that's the case, then I need to get this set up to our host, because this is an updated set, which I thought I had sent to him. Maybe he put the old one in. In any case, I'm going to make sure that this gets to him, so you'll have this when soon after the program's over. Otherwise, no, I'm pretty sure that can happen. Let's check watch the chat box. We'll see if the host is picking up on this, and maybe he'll put a message in the chat box about how we're going to deal with this. All right, thanks for calling us to my attention. What we're seeing show you exactly what we're looking at. What would be included in the uninterruptible loads? Well, and again, it depends on the size of your storage. And if you've got, let's say, these storage units come in, I think, 17.5 kilowatt hour You can get up to 18 in a single storage, and you can use a couple of them. So again, depending on the storage, that's going to limit the power rating of what you can have for uninterruptible loads. And it's all totally dependent on how much storage. And typically, with enough storage, you can supply 40, 50, and sometimes 60 amp loads. But again, it's dependent on the kilowatts and the kilowatt hour rating of the storage. And the storage is expandable. Certainly, the uninterruptible loads, you're going to want your refrigerator and maybe a TV set so you can see what's going on, and a computer. And, you know, that's your choice, your microwave oven, maybe garbage disposal and dishwasher, who knows what. Well, nice to have a washing machine that you can plug in from time to time and wash some laundry if you've got water. So yeah, that's the owner's choice. And once you define the uninterruptible loads, then you know how much storage you need. So that's what we went through here, Jerry, is to make sure that you know what to change if you want to make something different from what's already there. Okay, so this case, we have DC input to the inverter rather than AC input. And that means we don't have microinverters, but instead we have optimizers. And the optimizers, they are DC to DC converters that do maximum power point tracking. That's what it's all about. So if one of these things is shaded, these modules are connected in series, whereas with a microinverter circuit, the modules are connected in parallel. And they all run at 240 volts, or 208 if you happen to get that model. But with this one, the modules are all connected in series, and that means the optimizers are connected in series. So therefore, the current is the same in every module. So therefore, it's going to have to adjust the voltages on every module. If one of them is shaded, it's going to drop the voltage on that in order to be able to make up and have the correct current. And it gets even more fun when you have two strings, because then the inverter has to decide that both strings have to run at the same voltage. And they still have to have maximum power. So a lot of iterative calculations going on back and forth between the inverter and the PV optimizers. A lot of communication link there that doesn't show here. Okay, storage is DC. We talked about DC to DC converter. PV and storage are both connected to the same 400 volt DC bus roughly. So the inverter says, I'm going to maintain the voltage at around 400 volts if we can keep everybody happy with that, and sends that message down to all the modules and all of the optimizers, and they adjust their voltages and currents accordingly to try to make the inverter happy. And it's pretty fancy stuff, actually, but it works. And fairly efficiently as well. This inverter, the optimizers are rated at more than 99% efficiency. And the inverter itself is pretty high efficiency as well. So the advantage of the system, it's pretty high efficiency. It has single inverter that, rather than a bunch of microinverters, but it has optimizers up there on the roof anyway. And sometimes each individual module has its own optimizer, but there are also things called string optimizers that optimizes the performance of any single string, but not necessarily down to the module level. So, and that all depends on who the manufacturer is. But in any case, if you're doing string level optimization, then that string level is also going to do your rapid shutdown for you, and there are going to be little switches in line that will shut down modules when that happens. So this one, I think, is the Generac system. Yeah, this is the Generac system because they use string level optimization. SolarEdge uses module level optimization, but their configuration is just about the same. Okay, so here's an all-in-one DC coupled system. And that's a big inverter. That's a 7,600 watt inverter. Battery cabinets, here's the numbers I was looking for, 17.1 kilowatt hours. You can configure those cabinets with anywhere from 8.6 to 17.1. And there's two of them. So these are likely configured for 34 kilowatt hours of storage. That's pretty good backup. That'll back up most reasonable houses up to a couple thousand square feet. Batteries themselves are 46.8 volt, 3 kilowatt hours. So the cabinet has more than one battery in, doesn't it? If they're 3 kilowatt hours, that means you must have 6 batteries in each cabinet. Okay. And so the 18 kilowatt hour voltage would be 281 DC. And if you got 3 in series, and the round trip efficiency on batteries is 96.5%. Continuous battery power, 6.7 kilowatts. That's for the 17.1 kilowatt hour. So for two of them in parallel, that's double that. So that's a lot of kilowatts continuous power. That'll run a lot of stuff. And of course, you're not going to run that 6.7 kilowatts all the time, or you're going to run out of battery pretty fast. 6.7 kilowatt hours per hour, 3 hours, you're done. So inverters rated at 8 kW in the backup mode. That's one inverter. And most of the time, it's going to be running way below that. And the inverter is going to be perfectly happy. Something is telling me my interconnect connection is unstable. That's the last thing I wanted to see on my screen. I hope we are doing okay. Please hit that Q&A button if we have a problem with the internet. Okay. Anyway, the inverter's got all these important functions inside the inverter, all of them in that one cute little blue box. That's because the inverter doesn't have a big transformer inside of it. So those electronic components are pretty, and it's awfully efficient. And that in itself allows it to be smaller because there's not a whole lot of heat that's being generated. Okay, Dave says it's all good. Thank you. That's reassuring. Let's hope it stays that way. We've got now a little over 45 minutes or 15 minutes to go here. I'm proud of you all. It seems like pretty much everybody's staying awake here. And that's a good feeling. I'm doing my best to do the same. Yeah, I'm 79 years old and I'm supposed to always take my afternoon nap, but I'm trying not to do that today. Okay, so let's see what we got coming up here. What did I do? Oh, photo courtesy of Urban Solar. Urban Solar is a group that I was one of the people who convinced them to get into the solar business back in 2004. Here's some alternative battery backup design basics, okay? In other words, this is how most people do it now. Determine how many watts of solar you can put on a roof or the ground or wherever. Do that first. Then configure that array. And more than likely, that array is going to have modules with microinverters, which automatically says you're going to have an AC coupled system. Determine the system rated AC output power. Okay. Choose storage with AC output power rating at least 67% of the array AC rating. And again, this is 2 years old here for that because we've now got, you don't have to do that anymore. There are different limits. We'll come to that in a minute. But what this is saying is that the array, the AC output power of your array with the microinverters should not exceed 150% of the storage rating. All right, so if you've got the power that you can get out of your batteries is, say, 2,000 watts, then you don't want your array to be more than 3,000 watts, because that would be 50% higher than the rating of the batteries. Okay, so then we look at all the overcurrent protection that's needed for the storage AC output, and that's if you got a 10 kW unit, chances are that's going to be a 10 kilowatt hour unit. That's maybe 16 amps, and that needs a 20 amp circuit breaker. You got 4 of those, and you're going to have 80 amps that you need, and you're going to have to combine those and then run 80 amps up to your system controller. But we haven't seen the system controller yet, so we need to look at that. Let's look at the Q&A. How many watts per square foot? Okay, let's see if we can do that really fast. We're looking at the maximum solar intensity is roughly a kilowatt per square meter. Okay? If we're talking about an array that has 20% modules, 20% efficient, that means you can collect 200 watts per square meter with your array. Square meter is about 10 square feet. So that's 200 watts per square meter, which is about 20 watts per square foot, give or take a few. Is that close enough without my calculator in hand? We do a straight grid connect. You can imagine if I tried to include straight grid connect with how much of this stuff there is for 2 hours, including that, there's some stuff we just can't include everything. If you want to know more about the watts per square foot thing and the array sizing and that sort of thing, you might want to consider signing up for the Straight Grid Connect webinar. And we cover a lot of that stuff in gory detail. Another question, let's see. Close enough. Okay, good enough. All right, so what's total overcurrent protection? Well, if we got 4 units at 20 amps apiece, we're going to need 80 amps of storage AC overcurrent protection. If we're doing a bunch of power walls, each one of those takes a 30 amp breaker, 2-pole 30 amp. Interesting thing too, with these things with AC storage, the power walls have internal inverters that the output of the power wall or the input is at 120, 240. They actually have a neutral. Whereas if you have most of the other vendors have straight 240 volt AC for their backup, N phases, for example, you're looking at 240 volts, 16 amps for their 10 kilowatt hour backup unit. Just need to determine your fuse size, your circuit breaker sizes, and then what do you need for your AC output? And the controller for the N-phase system limits your AC output to 80 amps. And there's a reason for that. The controller itself is where the neutral is formed with an auto transformer. And if you dump in more than 80 amps at 240 volts, you don't necessarily have the capacity or capability to have different loads on the 2 different 120 volt legs of a 120, 240 volt output to feed your standby panel. So there's interesting situation there that you need to watch for, and there's maximum that you can put into that panel without overloading the transformer. Partial or full backup, and we've discussed that in some detail now, that full backup, you're probably going to want to have minimum 20 kilowatt hours of battery backup, and 30 or 40 is even better if you've got anything bigger than a couple thousand square feet. And if you're really fussy that you want to back up your 5-ton air conditioner, then you're going to need at least 40 kilowatt hours probably, just in order to get enough kilowatts for a 5-ton. 5 ton. If you got an SAER 12, you're going to need at least probably about 5.5 kW at least to run that thing. So you got to make sure you got that there. All right, so then you finish the design. And if you need an automatic utility disconnect, that may be in a system controller. And so you make sure you've got that. And then you figure out how you're going to connect to the utility. So let's do one just for the fun of it. You find a roof. Oh my goodness, this looks just like it's looking for a PV array, doesn't it? Well, let's put some modules on then. What do you say? How about like that? All right, by the way, this dotted line says that the so-called the small letter A and quotation marks out of that you find in ASCE 716 maximum design loads thing. So every good PV engineer has a copy of the National Electrical Code and a copy of ASCE 716 either on their computer or sitting on their bookshelf with maybe nothing else on the bookshelf. But you add the modules, as many as you can. And this is a south-facing roof, but who knows? Maybe you want some on the east-facing too. There's plenty of room there. And maybe some on the west. And, well, maybe even some on the north-facing roof. Surprisingly enough, it is now cost-effective in a lot of areas. You can make electricity amortize over the life of the system for about 8 or 9 cents a kilowatt hour. And if you're paying 15 cents a kilowatt hour, it's highly likely, if it's the only option, you'll stick a few modules on your north roof. And you lose about 30% by doing that, but you still make electricity. And the east and west, you're losing around maybe 15%. But again, if you need that electricity, you just scale up and your cost per kilowatt hour goes up by maybe 15%, but 15% more than 7 is still not 15 cents. So the old thing about let's put them all on the south roof, that's when they were $100 a watt. They're about 40 cents a watt now. So, that's a big difference. So this is what we're going to see. Now, what else we got? We got to figure out how we're going to hook them up. Well, this might be one way to do it. Here's some strings. The ones mean string number 1, 2, 4, 6, 8, 10, 12 modules. String number 2 has got 2, 4, 6, 8, 10, 11 modules. Different numbers. It's okay to do that. 4, 6, 8, and 3, and 8 more and 4. It's okay to do that with microinverters, okay, because they are in parallel. They are current sources, and they connect in parallel all at 240 volts AC on the wiring, which is open wiring, rated for being in open air. And as a result, it you don't have to derate it for conduit or anything like that. And at some point, it goes into a junction box and it goes downstairs. So here's your system on your roof. And how many modules we got here? We got 4, 6, 8, 16, and what do we got here? We got 24, something like 5, 10, 13, a lot of them, all right? If these microwave inverters are 290 watt, and that's kind of small, more likely they'd be, for this size, by the way, this geometry, it'd probably be more like at least 330 now, but there's lots of 460 watt modules out there even that can go on roofs, but they're bigger than these, geometrically. In any case, you got 290 watt microinverters then at 240 volts AC and 1.21 amps. Oh, I'm sorry, a 290 watt microinverter, not 290 watt modules. I must be getting, somebody should have caught me on that. My goodness. Here, Q&A 3, let's see what we got. We found on most heat pumps, not the new inverter driven one, startup current can easily be 4 times running current on most heat pumps. Yeah. And some of the manufacturers of solar, they actually have soft starters that you can use to lower the inrush. So yeah, this is definitely a consideration, Dave. And If you're trying to run a heat pump or an air conditioner or anything else that has a high locked rotor current, you may need to look to make sure the manufacturer has a soft starter kit. And Enphase has one of those, and a number of others do manufacture. So just Google soft start kits, and they'll take care of that for you. You can store up a little bit of, if you have a little bit of storage, battery storage, or if you simply don't give it the full torque for the starting, start up a little slower, you can beat that problem. Let's see what else we got. Dave, why do you not need a derate conduit on a roof? Oh, well, these modules are wired with open wiring. Yes, once the open wire is run into conduits, and you have junction box up there, and you run the open wiring in, and you splice it with the wiring that the THWN2 that's going to be in the conduit that goes downstairs. And yeah, then you have to derate it for conduit fill and for temperature. Important to note that if you keep that conduit 7/8 of an inch above the roof, the temperature derating is merely the ambient temperature now. There's no fancy stuff like there used to be. And so then you just got your derates for 4 to 6 of 0.8, 7 to 9 of 0.7, and 10 and more is 0.5. And yeah, you do need to derate if it's coming down. And those are your numbers you're going to use. So thanks for reminding me of that. I should have mentioned that sooner. And I didn't mean to, I'm afraid I may have said something that would not understood. Is there a cost estimate for equipment available for quoting on a known example or a rough estimate? Let's just say a total system without batteries typically goes in for, in my neighborhood, the cost without the government tax credit is roughly $3 a watt. Now that's just for that, that's total cost. So that's a total installed cost. And then with the 30% tax credits down to $2.10. I'm not sure what that's total installed cost. The equipment, I just saw a set of equipment priced out yesterday without batteries. It was just a little bit under $1 a watt for all the nuts and bolts and no storage. But then the storage, everybody's storage price is ever so slightly different, but somewhere in the neighborhood to 12 to 15,000 for 10 kilowatts worth of storage, and some are less expensive, some are more. You need to do a little shopping around for that. But look for warranties and other things as well. And before you, you can buy a cheap car or a more expensive car, and well, sometimes more expensive ones are a whole lot more expensive to keep up as well. So price is not necessarily everything. Okay, missing this one and the previous one. So obviously you got the previous presentation. I need to get this up to the host, and I'm sure he'll make arrangements to make sure that you get these one way or another. If nothing else, he'll give you my email address and all. You can email me and I'll send it to you directly. Hisham, if you hear that, it's fine if you want to give out any of my email address to anyone if they want some material, but it's not. But I'm going to send some up to Virginia, and so he'll have some available. Okay, missing that. Okay, got that. I'm sorry that happened. Okay. Oh yeah, and that 75-page download is there with a bunch of extra stuff that we absolutely. Yeah. Okay. $3 a watt, Dave. Okay. Sounds good. Yeah, there's more stuff that comes after the end of this that I put into this an appendix, because there's a lot of stuff and I want you to be able to have it. So there will be more answers. All right, here's the microinverter, 290 watt. Let's call it an IQ 8 plus, and 1.21 amps, 240 volts. So now we can figure out what do we got on the roof. A 20 amp circuit allows 13 of these modules per circuit because you can't exceed 16 amps, or in other words, you need 125%. Your overcurrent protection and wiring has to be at least 125% of your maximum current. And so we're at 19.7 amps, 20 amp overcurrent. Okay, good. And now let's do some more math. We combine these circuits, 8, 8, 12, 12, all the total current coming in. We got 48.4 max coming out of that combiner, which has communications, which talks to each microinverter separately and monitors the output from each of them. And if there's a problem, it reports it to you and to the company, and you get an email saying, hey, so when these go in, you put them in with a map of which is where, and that gets stuck into the communication lane. So you can see that these are current sources. They're all running at 240 volts, but they can run at different currents if you have different numbers of modules. And this is maximum current. It could be less than that if there's one of these modules is shaded, or if it's later in the day or earlier, if it's warm outside, whatever, it probably will be less. But that's okay because we're looking at the total kilowatt hours production, not the instantaneous kilowatt production. So here we go. We're connected in here. I think I know what happened too. I think somehow or other the previous presentation, this was redone with all these cute little drawings here back in 2021. And I think we just need to make sure you all get the 2021 version in your hands or on your computer. You probably can't touch it. All right, 370 watt modules. Now we're getting down to good size. We got 40 of those. There you got 14,800 watt system. That's a dandy, isn't it? If we have 290 watt max microinverters, we got 11,600 watt system. Believe it or not, we got DC-AC ratio at 1.28. Very nice system. And it's pretty typical for what's going into residentials now, right down in my neighborhood. And I'm guessing yours might be about the same. So this is a pretty common system. We got 6 chats. Is this, let me just take a quick look. Yeah, David, are we after 4 o'clock? Oh, yeah, absolutely. You get credit because we're about done here too. I'm going to click here as quickly as we can. We had a little more discussion than I anticipated, which is good, but then we end up going a little quicker. So let's just click on through. The whole thing, DC to AC ratio of microinverters is useful to go through because here we're looking at a single microinverter, 290 watt microinverter connected up to modules of different sizes, okay? And this is what happens if you do simulation. It's almost linear. In other words, you can connect up a 440 watt module to a 290 watt microinverter, and most of the time that 440 watt module is not putting out any more than 290 watts. If it were, that line would not be straight. So that's why you can feel confident about using a 290 watt microinverter, at least in your neighborhood. And the thing to do if you're not sure is do this simulation and see whether you're somewhere where you are going to overload it. But this is for down my neighborhood here, and this is what happens. This works here. What else we got here? Mentioned starting in 2020. Oh, not that the utilities are requesting power, but they may. And some I think maybe are. And not just power, but yes, energy and power factor control from the utility can be done. Not very many people are doing it yet, but most of the inverters produced since 2020 do have this capability of doing that, and they can export power, and they can even control power factor. We did a bigger 5.5, or well, I guess they're a 2 and a 3 megawatt system, and the power company wanted to have power factor control between plus or minus 0.9, and so, you know, if they want that, you need to pay a little bit of attention to making sure your wires are okay to manage that. But normally, if your power factor drops to 0.9, then the output power drops a little bit along with it, so the line currents don't really change a whole lot. and they don't go over the max. All right, so let's see quickly. Minimum recommended storage. Okay, you can read this when you get the presentation. Decide what backup, whole or otherwise. Configure the system. Here we go. Here's your system controller. Here's where your batteries tie in, going with 20 kilowatt hours of storage. This is a partial backup here. That's the main distribution panel, 175 amp main breaker. Oh, you need your, there's certain rules here of interconnect that we don't have time for today, but NEC 705.512 and 705.511 have all those rules. And your system basically is going to look something like this. The pink thing is the system controller. And that's the thing that senses when the utility goes down, and those contacts with the line through are the ones that disconnect from the utility when the utility goes down and feed all of the available power from storage and or modules down to the backup loads. And if the backup loads can't use all of it, then they cut back on the power output from the modules so that they don't overcharge the batteries. So that's an important consideration on an AC coupled, that when the utility is down and the sun is up and you don't need all the electricity you're making for loads and battery storage, your controller has to shut down on the module output or you damage the batteries. That's not a good thing. So there's the modes of AC, and here's the Powerwall diagram. Looks a lot. It's AC coupled, as we pointed out, and okay, that's what it looks like. There's what the parts are all about, and this is it for the day. There's more. I apologize. There's more. You've got all the material. You're going to have this all if you get the slides. And I'm going to have to make a decision whether to cut out some of that earlier stuff and keep the other stuff, or to leave it as is, being with the faith that people can read it. And any comments you might be able to feedback, I'm amenable to making adjustments to make this thing as useful as possible. I hope you've gotten something out of it. I'm going to stop the show right here. And because we are now at 4:08 and some people have to go, that's fair. So let me say thank you to everybody for coming. And I hope you got something useful out of this, this session. And any comments are more than welcome on how you might like to see, if you'd like to see less of the older stuff and more of the newer stuff. I think I might be, anyway, we got to go. We got to let you go. So thanks for being here. And let's see, I don't want to close that off. I want to close this off so I can see my screen. Okay, at this point, I see 3 questions. Let's see what we can do. Okay, thank yous. And you're very welcome. There's things in the chat. I'm going to watch the Q&A box until everybody signs out in case there's something we missed that you might like to talk about before we all go home and have our dinners.